So in this problem, we're asked to calculate the pH of a solution that's prepared by mixing 5 milliliters of a 0.1 molar sodium hydroxide solution with 5 milliliters of 0.1 molar acetic acid. Okay, so with all of these problems where we have to calculate the pH, the first place we want to start is with a balanced reaction. So we're going to write our balanced reaction for this process. And so we're mixing sodium hydroxide. So we're going to say NaOH aqueous with acetic acid. So CH3COOH aqueous. Now, when I draw my reaction arrow, when we look at our reactants, acetic acid is a weak acid, but sodium hydroxide is a strong base. So once one of your reactants is a strong acid or strong base, that's telling us we're going to use a one-way reaction arrow. And so again, that's a one-way arrow because strong base is present in our reactants. So our products of this, we have our base with our acetic acid. So the hydroxide and the acidic proton is going to form water. And then we're going to be left with our CH3COO minus acetate anion. And then we just have our spectator sodium ion, which I'll keep just to balance the reaction. So here's our initial balanced chemical equation. So again, we're in a situation where we performed a reaction and we did not form any hydroxide and we did not form any hydronium. However, when we look at the products, what we need to recognize is the product of this reaction is in fact the acetate anion, which is a weak base. And so in order to find the pH of the solution, it's actually going to be a weak base equilibrium. But before we get there, we need to go through the stoichiometry of this reaction to figure out how much acetate was formed. So the way we do this, again, is because we have a strong base and a one-way reaction arrow. I'm going to use my before and after table. We'll calculate how many moles of things do we have before the reaction and how many moles of things do we have after the reaction. So down below we can find moles. Here we can find the moles of sodium hydroxide and of acetic acid. And the way we find moles is we're going to take our concentration times volume. So for sodium hydroxide, it's going to be 0.005 liters times 0.1 molar. And so we get 0.0005 moles. And we'll notice acetic acid is going to be the same thing because we have the same concentration and same volume. So acetic acid, we're also going to end up with 0.0005 moles. So before the reaction takes place, we have 0.0005 moles and 0.0005 moles. So 1 to 1 mole ratio, they're the same amount of moles. So after the reaction takes place, those are both gone. On the product side, the water we don't really care about, the sodium we don't care about. Initially, we have no acetate, but after the reaction, we're going to form some, and we're forming 1 mole of acetate for every 1 mole of acetic acid that reacts, and so we're going to end up with 0.00005 moles. So that tells us after this first reaction takes place, this is how many moles of acetate we have in solution. What we now need to do is convert that into our concentration, right? So we're going to find the concentration of CH3COO minus is going to be the 0.0005 moles divided by the total volume, which in this case can be 10 milliliters or 0.01 liters. And so our initial concentration is 0.05 molar. So this question that we were posed up above, really what it's saying is, when we get to here, is what is the pH of a solution that is 0.05 molar in acetate. And that is a problem that I hope you recognize we've done a bunch of. So how do we solve that problem? We're going to start by writing about a chemical equilibrium, because now we have a weak base, starting with our acetate. Weak base plus water goes to acetic acid plus our hydroxide. In this weak base equilibrium, Kb is equal to CH3COOH times hydroxide over our acetate. We can now set up our ice table and plug in what we know. We're starting with 0.050 molar of acetate. We don't care about water. We have no acetic acid, no hydroxide. Our change then is minus x, x, and x. So at equilibrium, we have 0.050 minus x, x, x. So from there, we can say Kb, which you can look up from tables, is 5.5 times 10 to the minus 10th. Again, I looked that number up. It's equal to x squared over 0.050 minus x. Now we can go through the process of solving this. So again, at this point, we can make our assumption, assume that 0.05 is much bigger than x, and we can make that because this is a very small number, so we're going to form very little product. If we do that, then our expression simplifies to 5.5 times 10 to the minus 10th equals x squared over 0.05. We can go ahead and solve for x. I'll let you do the math. You can pause the video and do that. I got 5.2 times 10 to the negative 6th equals x. If you make an assumption, we need to check it. So to check it, we're going to do a ratio of 5.2 times 10 to the minus 6 over 0.05 times 100, and that is 0.01, which is less than 5%. So our assumption is valid. Which means we can now get back onto saying, well, this is x, and we know from our equation, here's x, so we can see the concentration of hydroxide we have defined to be x. So if we find the POH now, which equals to the negative log of our hydroxide, so POH equals negative log of x of 5.2 times 10 to the minus 6. POH is then equal to 5.28. 14 minus that, we can find the pH is equal to 8.71. And we find out it's a basic solution. So there's the answer. If we go back up to the problem, we found out our solution was basic. Way back here at the top, we asked, what will the pH be of a solution prepared by mixing sodium hydroxide with acetic acid? And what we can predict from this is we have a strong base with a weak acid. And so because we have a strong base and a weak acid, we should expect this to be basic. And indeed, it is basic. Thank you.